Hi, I'm Gabriel Low. Here I'll be walking through my undergraduate research into the development of a low-cost deployable seismic station. Why might it be useful to have a low-cost and deployable seismic station? Maybe not all funding institutions are able to invest money into the expensive upkeep and installation of full-on broadband seismometers. So here we're looking at those scenarios, especially when there are time restrictions or money restrictions. Now, the project goals are to build and test a deployable, meaning it can be taken out and put into the wilderness, deployed, low-cost, sub $1,000, IoT connected, somehow connected to the internet, and the other requirement is using commercial off-the-shelf components to build this prototype proof of concept deployable seismic station. Now, the core of this station will be the Raspberry Shake, a basic geophone digitizer to a Raspberry Pi seismograph that already is Internet of Things kind of integrated. So with that sensor, it needed to be adapted to become deployable. It needed the network connection, the cellular network connectivity, if it's going to be deployed out into an area, needed a weatherproofing case as well as a power supply. So that's where this graphic here to the right shows the flow of how those components were selected, all commercial off the shelf, with a ultimate cost of $563, so well under our $1,000 goal. Through testing, we found that the components chosen worked well. There were a few moments where this could have worked better. Namely, the two largest were in the battery. The battery was able to power the Pi for an average of 31 hours, which was able to send data during that time, and it worked well. However, we were hoping for at least 48. So perhaps the solar panel on that battery did not work as well as we hoped. Now, the other part that we weren't expecting was that the LTE USB adapter, the USB that connected the Shake, basically turned it into a cellular mobile device with data, was not able to connect to the Raspberry Shake server. So with a workaround there, we set up a virtual local area network and we're able to receive data here on a Raspberry Pi locally and process that data with a software program called RSUDP. This program was able to receive that data for the whole 31 and a half hours during two tests that we conducted here in a local residential backyard in Anchorage. The program had an earthquake alert algorithm running. Unfortunately, no earthquakes were detected. This could be for a few reasons. Most likely because it was placed on a very, very soft substrate on some topsoil and some vegetation we see in this image here. That kind of dampened a lot of the earthquakes that may have been coming through, and the fact that the software maybe needed some tweaking in the settings for the detection. Now, in the conclusion, we were able to successfully have a proof of concept deployable seismic station. However, for further application and real world use of this prototype, further investigation is needed, both with better testing scenarios and comparative analysis of other higher cost solutions. Now, I'd like to thank my mentor and a number of other people who helped me on this project. It's been a blast, and thank you.